Hi, this lesson is about L'Hopital's rule and determining the indeterminate form. So L'Hopital's rule is a rule that allows us to evaluate limits as long as the limit is in what we call an indeterminate form. So there's many types of indeterminate forms, but the most fundamental ones are when your limit is a quotient of two functions where the limit of the numerator function and the denominator function, if those both equal zero, so that would be type 0/0, or if both the limit of the function in the numerator and the limit of the function of the denominator, if they are approaching either plus or minus infinity in the numerator and the denominator, well, that's the type that we're calling plus or minus infinity. So the signs do not have to be the same, and they do not have to be different. So you can have infinity over infinity, or you can have infinity over negative infinity, or negative infinity over infinity, or negative infinity over negative infinity. So, so that's the first thing you need to do before you apply L'Hopital's rule. So let's talk about what L'Hopital's rule is. L'Hopital's rule says that you can evaluate a derivative as long as both are differentiable of f and g prime is not equal to 0 on an open interval that contains some value a, and a is the value that the limit is approaching. So as long as they are in indeterminate form, then this is what L'Hopital's rule says. It says that the limit of f of x over g of x as x approaches a is equal to the limit of f prime of x over g prime of x as x approaches a, as long as those derivatives exist. Now, by taking the derivative of the numerator and the denominator, it often leads to something where direct substitution can be applied. And in other cases, you might have to apply L'Hopital's rule more than once. So you'll see an example or two of that. So here's our first example. I have the limit as x approaches pi of 3 cosine of 3x plus 3 over x minus pi. So first, let's figure out the indeterminate form. So you cannot use L'Hopital's rule automatically until you prove that it's either in the form of 0/0 or plus or minus infinity over plus or minus infinity. So by doing direct substitution, so right here I'm plugging in pi for x. So I get 3 cosine of 3 pi plus 3 over pi minus pi. So cosine of 3 pi is -1, so I'm left with -3 plus 3 over pi minus pi. And when you simplify, you get indeterminate form of 0/0. This is not an answer. This is just proving that now you can apply L'Hopital's rule. So now we use L'Hopital's rule. So notice that I'm using this notation. So not everyone uses this notation, but I prefer it because this is where I can see that you are applying the actual rule. So I put a little h on top of the equal sign for L'Hopital's. So I have the limit as x approaches pi. And now what you see on top is the derivative of the numerator of the original expression. So you have to apply chain rule. So I have 3 times negative sine of 3x times 3. So that's chain rule applied to this part of the numerator. And the derivative of 3 is just 0, so you no longer see that in this line here. And the derivative of your denominator, well, that's just 1 because the derivative of x is 1 and the derivative of pi is 0. All right, so if I simplify this line and move on here, I have -9 sine of 3x, and you no longer need to write 1. So at this point, direct substitution will work fine. So I plug in the pi in for x, and you have -9 sine of 3 pi. Sine of 3 pi is 0, so your answer is just 0. All right, so here's another example. I want to evaluate the limit as x approaches infinity of ln of x squared e to the over e to the 2x. So what's the indeterminate form? So we're right here. Indeterminate form, so if you were to plug in infinity, natural log of infinity squared is just infinity. Remember the natural log function just keeps increasing. So I'm going to draw it over here. So as x gets larger, ln of x gets larger as well. So does ln of x squared. It just grows a little faster. And e to the 2x, well, e to the 2x would look like this. So as x gets larger, e to the 2x also grows actually much faster than ln of x. So this is of the form infinity over infinity, right? But you cannot assume that infinity over infinity is equal to 1. A lot of people want to say that. Well, they're both growing to infinity, so it must equal 1. But that's actually not true because it depends how fast one is growing compared to the other. You can see from the graphs that I drew that ln grows much slower than e, much slower than e to the 2x. So this is actually a false statement. So that means that I can apply L'Hopital's rule. So again, I'm here where I drew my H. Let me just change the color of this so it's easier for you to see what I'm doing. Okay, make it green. So here I have, I'm applying L'Hopital's rule. And so I take the limit as x approaches infinity. And the numerator, the derivative of the numerator is 2 times 1 over x. So you can get to this derivative by using chain rule on ln of x squared, or remember that ln of x squared is the same as 2 ln of x. So when you take the derivative of 2 ln of x, that's just 2 times the derivative of ln of x, so it's 2 times 1 over x. And the derivative of e to the 2x, well, here you have to use chain rule. So that's e to the 2x times the derivative of 2x, which is 2, which leaves you with this result. So from this line to the following line, all I'm doing is simplifying. The 2's will cancel each other out. And the 1 over x, well, that x ends up in the denominator with e to the 2x. So I have 1 over x e to the 2x. And as x approaches infinity, well, that means I have 1 over a very large number, which means the whole thing equals 0. Okay. So we want to evaluate the limit as z approaches 0 from the right of ln of 4z over cosecant of z. So this is indeterminate form of negative infinity over infinity. So again, as a reminder, what does ln look like? Ln of 4z looks a lot like ln of z. As you get closer and closer to 0, on the right side of 0, this is approaching negative infinity. And cosecant, well, remember cosecant is 1 over sine. So sine is equal to 0 at pi and here at 0. So again, let me use a different color here. At 0, so we have an asymptote here and here for cosecant. And at pi over 2, it has a value of 1. So hopefully you remember these graphs. Okay, and then on this side, it would look like this. Okay, we don't really need that to answer this question. But as z approaches 0 from the right, you can see that cosecant of z is approaching infinity, which is why you have negative infinity over infinity. All right, so all that tells us is that now you can apply L'Hopital's rule. So I have right here, I'm applying L'Hopital's rule. I have the limit as z approaches 0 from the right. The derivative of ln of 4z, when you apply chain rule, the 4's end up canceling, and you have 1 over z. And the derivative of cosecant of z is negative cosecant z cotangent z. So simplifying, that leaves us with the limit as z approaches 0 from the right of negative 1 over z cosecant z cotangent z. But you're not ready to apply direct substitution here because you would basically get 1 over 0, and we know that's, or negative 1 over 0, and we know that's undefined. So I'm doing a little bit of trigonometric substitutions here because 1 over cosecant of z is equal to sine of z, and 1 over cotangent of z, well, that's tangent, so that's sine of z over cosine of z. So I used those substitutions right here, where I drew this arrow. And so 1 over cosecant became the sine, so that's this piece right here. And 1 over cotangent became sine over cosine. And the z stayed put. So I have, so now I move on to the next line. I have negative z squared over z cosine of z. And we're taking that limit as z approaches a 0 from the right. But again, I can't apply direct substitution. And if you did, you would find that it is still in an indeterminate form of 0 over 0. So therefore, I can apply L'Hopital's rule again, which I do right here. So I have the limit as z approaches 0 from the right of negative 2 sine of z cosine of z. So I applied chain rule to the numerator. And in the denominator, I applied product rule. This here is my product rule. So I have f g prime plus g f prime. So that leaves us with negative z sine of z plus cosine of z. All right, so at this point, I am going to apply direct substitution. Direct substitution will no longer result in an undefined expression. So I have negative 2 sine of 0 cosine of 0 over negative 0 sine of 0 plus cosine of 0. So remember, when you apply direct substitution into your limit, you are no longer writing your limit in front of the expression, you're just evaluating it. And if it's not an indeterminate form, what you get is your answer for the limit. So the numerator works out to be 0. My denominator works out to be 0 plus 1, so it's just 1, and 0 over 1 is equal to 0. So first 3 examples all had an answer of 0. That's not always the case. So we'll see some other possibilities in these next few examples. So the next few examples are other types of indeterminate forms. These are a little bit more work to manipulate. So the first possibility is if you have an indeterminate form of infinity minus infinity. The second one would be 0 plus or minus infinity. So the infinity could be either approaching positive or negative infinity. The third one is if you have 0 to the 0 as an indeterminate form. And the last possibility here would be 1 to the infinity. So if you look here on the right, and I'm going to use a different color just to kind of make things stand out. So if you look here on the right where I wrote this note here, if the limits are of these other indeterminate forms, they must first be rewritten as a quotient. Then identify the indeterminate form of either 0 over 0 or plus or minus infinity over infinity before you apply L'Hopital's rule. So before applying L'Hopital's rule, you basically have to be working with a quotient that is in one of the indeterminate forms that we just talked about before. All right, so let's move on to this example right here. I have to evaluate the limit as theta approaches pi over 2 from the left of tangent of theta minus secant of theta. So if you were to directly substitute, you would get that the indeterminate form is infinity minus infinity. Now, it really helps if you know your graphs for these types of functions. So tangent is undefined at pi over 2. So when you are on the left side of pi over 2, tangent is approaching infinity. Okay, now secant is the reciprocal of cosine, and cosine is also undefined at pi over 2. And at 0, it has a value of 1. So here I have my asymptotes. And your secant function looks like this. To the left of pi over 2, and then remember it does this, it oscillates like this for every pi units like that. So this is definitely approaching infinity. Both tangent and secant are approaching infinity when you're on the left side of pi over 2. All right, so now the limit must be rewritten as a quotient. So I'm reminding you of that here. So this one actually isn't too bad to rewrite, because if you rewrite tangent as sine over cosine and secant as 1 over cosine, then you naturally have a common denominator of cosine. So I'm here at this point. I have the limit as theta approaches pi over 2 from the left of sine of theta minus 1 over cosine. So if you were to plug in pi over 2 into the this expression, you would find that it is of indeterminate form of 0 over 0, which means we're ready to use L'Hopital's rule. So I apply L'Hopital's rule right here. I take the limit I take the derivative of the numerator. So the derivative of sine of theta minus 1 is cosine, and the derivative of cosine is negative sine. So I'm left with this expression, negative cosine of theta over sine of theta. And here I can apply direct substitution. So I'm left with cosine of pi over 2 is 0, sine of pi over 2 is 1. So negative 0 over 1 just gives you a value of 0. All right, so here's another one. And I promise the answer here will not be 0. So I have the limit as x approaches infinity of 5x sine of 1 over x. So by direct substitution, if you were to substitute infinity, well, 5x goes to infinity. And sine of 1 over x, we know that 1 over x as x approaches infinity, well, that goes to 0, and sine of 0 is 0. So this is indeterminate form of infinity times 0, which was one of the possibilities that I gave you. So now we're ready to rewrite the limit as a quotient. So even though you have a quotient in your original expression, 1 over x is a quotient, the entire expression is not a quotient. So we're just going to use what we know just from algebra. I know that I can write x is the same as 1 over x. So that's what I did right here. Instead of writing 5x sine of 1 over x, I put the x below and wrote it as 1 over x. It still equals the original expression. It just allows me to rewrite it as a quotient. So now from this line to this line right here, I'm just going to rewrite 1 over x as x to the negative 1 so that I can easily take the derivative when I apply L'Hopital's rule. So here on this line, I'm applying L'Hopital's rule. So to take the derivative of the numerator, you have to use chain rule. So it's 5 times the cosine of x to the negative 1 times negative x to the negative 2. So negative x to the negative 2 is the derivative of the inside of the sine function. And the derivative of the denominator is just power rule. That's also negative x to the negative 2. So, but something interesting happens here. The negative x to the negative 2 cancel each other out. So I'm left with this limit. I have the limit as x approaches infinity of 5 cosine of 1 over x. And here you can apply direct substitution. As x approaches infinity, 1 over x goes to 0. So I have 5 times the cosine of 0. Cosine of 0 is 1. 5 times 1 gives you a limit value of 5. All right, so here's another one. I want to evaluate the limit as x approaches 0 from the right of 1 plus sine of 4x, and that expression is raised to the cotangent of x. So here, by direct substitution, this is equal to, this gives you an indeterminate form of 1 to the infinity. So let's look at where does the 1 come from. When you plug in 0 right in here, sine of 0 is 0, so 1 plus 0 is 1. So that's where the 1 comes from. And cotangent at 0, well, again, it helps if you know what the graph looks like. So cotangent, remember cotangent is equal to cosine over sine. So everywhere that sine is equal to 0, your cotangent function will be undefined. So it is equal to 0 at pi and at 0. And here at pi over 2, it has a value of 0, okay? So here's one iteration of your cotangent function. So as you get closer and closer to 0 on the right, your cotangent function is going to infinity. So that's where the indeterminate form comes from, of 1 to the infinity. So with these types of limits where you have 1 to the infinity, you're going to want to use your natural log function in order to move the exponent out of that position. So we're going to use a little trick here. We're going to let y equal the expression that you're taking the limit of, and then you're going to take the natural log of both sides. So I'm right here. So I have ln of y is equal to ln of 1 plus sine of 4x to the cotangent of x. So from this line to the next, so I'm down right here, cotangent of x goes in front of the natural log because of the log laws. So I end up with a product, cotangent of x times ln of 1 plus sine of 4x. Well, we need to take the limit of that. And if you were to consider direct substitution, this would be still an indeterminate form of infinity times 0, but it's not a quotient. And so we know that we still have to do some manipulation. Okay, but again, trigonometry gives us a lot of options because all trig functions can get rewritten in terms of another. So from this line to this right here, I rewrite cotangent of x as tan of x in the denominator. So now I have a quotient, the limit, as x approaches 0 from the right, of ln of 1 plus sine of 4x over tan of x. But by direct substitution, you will find that this is also indeterminate form of 0 over 0, which means we have a quotient, it's in indeterminate form, we are ready to apply L'Hopital's rule. All right, so we move on, and here we're applying L'Hopital's rule. So I'm on this line right here. L'Hopital's rule means you take the derivative of the numerator, which is chain rule. So it's 1 over sine of 4x times the cosine of 4x times 4. So you have 3 layers on the top, the ln, the sine of 4x, because the derivative of 1 just goes away, and then the 4x, which gives you that last derivative right here of 4. And then the derivative of the denominator is secant squared. Okay, so moving on to the next line, I just organized it a bit, so we're not applying L'Hopital's rule here, we're just making it look a little better. So I have 4 cosine of 4x in the numerator, the 1 plus sine of 4x and the secant squared end up together in the denominator. So now I'm ready to apply direct substitution. So by direct substitution, here you end up replacing all of the x's with 0. And when you simplify, you get 4 times 1 over 1 times 1, and the whole thing equals 4. But that's not equal to what you were originally trying to find. So recall that we took the natural log of both sides of this equation right here. So therefore, the 4 means that ln of y is equal to 4. And so if we're solving for y, you're going to take e, and so we have e raised to the ln of y is equal to e to the 4th, and e to the ln of y is just y, so y is equal to e to the 4th. Therefore, the limit as x approaches 0 from the right of 1 plus sine of 4x to the cotangent of x has a value of e to the 4th power. All right, so just to summarize what we did above, you're going to apply the same technique whether you have 0 to the 0 or 1 to the infinity. So to evaluate limits of the indeterminate form, whoops, misspelling here, indeterminate form of 0 to the 0 or 1 to the infinity using L'Hopital's rule, you're going to use the natural log function to help you rewrite the limit as a quotient before you apply L'Hopital's rule. So the trick we applied above of letting y equal your limit and then taking ln of both sides will be done whether the original indeterminate form is 0 to the 0 or 1 to the infinity. So this next one is a 0 to the 0 example. So we want to evaluate the limit as x approaches 0 from the right of x to the x squared. So if you were to apply direct substitution, that is indeterminate form 0 to the 0. Okay, so that tells you I need to use that trick that we applied above. We're going to let y equal our limit. So y equals the function that we're taking the limit of. Y is x to the x squared. Take ln of both sides. So I have ln of y equals ln of x to the x squared. The x squared becomes now goes in front of the ln. So you have ln of y equals x squared ln of x. Okay, so this is what we want to take the limit of. So the limit as x approaches 0 of x squared ln of x, again by direct substitution, this would be indeterminate form of 0 times negative infinity. Again, recognizing the graphs of your ln function, as well as all the trig functions that we talked about before are really helpful. And then we know that we still don't have a quotient, so we're going to use what you know about your exponents and their rules. So the limit as x approaches 0 from the right, well, that's ln of x over x to the negative 2. So by moving the x and putting it in the denominator and changing the sign to a negative 2 instead of positive, well, that's equal to the above line. They are equivalent, just written in a different way. Okay, but writing it as a quotient allows us to evaluate this to see if it's indeterminate form. As x approaches 0 from the right, ln of x goes to negative infinity, but 1 over x squared becomes 1 over a really small number, so that goes to positive infinity. So this is indeterminate form negative infinity over infinity, which means we can use L'Hopital's rule. So now I'm here. All right, so L'Hopital's rule, I take the limit as x approaches 0 from the right of 1 over x divided by negative 2x to the negative 3. Little typo here. I'll have to fix this as we're moving along. And then if I rewrite this so that I can cancel my x's, I have 1 over x divided by negative 2 over x cubed. But dividing by a fraction is the same as multiplying by the reciprocal of that fraction. So I have the limit as x approaches 0 from the right of 1 over x times negative x cubed over 2. And if you simplify the x's, you get the limit as x approaches 0 of negative x squared over 0. Here you can apply direct substitution and you get that the value is 0. But again, that's not the answer to your to what you were originally asked. You were asked to evaluate the limit of x to the x squared, and remember we took the ln of both sides, so I have ln of y is equal to 0. Again, raising e to the ln of y and e to the 0 will allow us to solve for y, and so y is equal to 1. Therefore, the limit as x approaches 0 from the right of x to the x squared equals 1. Okay, so now you should try doing your 4.4 homework on L'Hopital's rule. L'Hopital's rule is really important concept for you to know for future math classes. Good luck.